what, in your model, what happens to these suns when they supernova?
Everything gets old and die.
Everything gets old and die. And does everything recompress?
Has to. And you breathe out, what happens to that air? Another plant breathes that air in.
Imagine the brightest star in the night sky suddenly dimming. Now, imagine it exploding in a colossal supernova. This is the potential future of Betelgeuse, a red giant star on the cosmic edge. For millennia, we've gazed up at the night sky, finding solace and wonder in its constellations. But what if that familiar pattern, Orion, was on the verge of a dramatic and irreversible transformation? Betelgeuse, the red giant marking Orion's shoulder, is teetering on the brink. Are we standing on the precipice of witnessing a supernova, a celestial explosion that could change the night sky forever? Terrence Howard issues this warning: the universe is more volatile and unpredictable than we often acknowledge. Could we be witnessing the birth of a supernova, a celestial firework display unlike anything ever seen before? Betelgeuse's stellar journey. Deep within the constellation Orion, a cosmic giant stirs. Betelgeuse, a red supergiant star, is at a crossroads in its stellar journey. Recent observations paint a picture of a star in flux, its once steady glow now flickering with an unsettling rhythm. But what does this celestial dance signify?
Just from water, and there's no end, like with...
So it's a real lightning gun, like
Yes.
a quake.
Yes. So, and the patent's been granted. Typically, you're limited to how much charge you can put inside of a cartridge.
Could Betelgeuse be on the precipice of a monumental transformation, a cosmic spectacle etched in the annals of history, towering over our sun by a staggering 764 times? Betelgeuse is a behemoth. Imagine a celestial titan whose fiery embrace would engulf our entire solar system, stretching beyond Mars. The sheer immensity is a stark reminder of Betelgeuse's advanced age and the drama about to unfold. Betelgeuse, the crimson giant in Orion's shoulder, isn't just another star. It's a cosmic time bomb, nearing the end of a life far grander and more explosive than our suns. This red supergiant, a mere 8 to 8.5 million years old, practically an infant in stellar terms, has already exhausted the hydrogen fuel in its core. Now it undergoes a dramatic transformation, a fiery tango between expansion and cooling. Imagine a star so massive it could swallow our entire solar system whole. Betelgeuse dwarfs our sun by a factor of 764. This incredible size hints at a past spent blazing brightly as a blue giant, using hydrogen with ferocious efficiency. But time, the ultimate sculptor of stars, has transformed Betelgeuse into a cooler, redder giant. Its surface temperature, a mere 3,500 Kelvin, compared to the sun's 5,500 Kelvin, explains its distinctive ruby-like glow. But the story doesn't end there. Betelgeuse's current state signifies a crossroads. Is this a prelude to a colossal supernova, a celestial fireworks display that will reshape the night sky? Or is there another twist waiting to be unveiled in the grand narrative of this stellar giant? But this color is not just a visual trait, it provides clues about the star's physical condition and the processes occurring within its vast gaseous expanse. Betelgeuse, the fiery heart of Orion, holds a secret within its crimson glow. Historical accounts, whispers from the past, paint a surprising picture. 2,000 years ago, Betelgeuse wasn't the majestic red giant we see today. Ancient Roman and Chinese texts describe it as a vibrant yellow star. This shift in color across human history isn't a mere astronomical footnote. It's a window into Betelgeuse's turbulent past and a potential harbinger of its explosive future. Adding another layer of intrigue is Betelgeuse's ever-changing luminosity. Unlike our sun's steady brilliance, Betelgeuse pulsates in a celestial dance of light and shadow. This semi-regular, variable nature has captivated astronomers for centuries. Its primary cycle takes 400 days, with a larger 5-year rhythm woven into its luminous tapestry. Evidence of these cycles stretches back to Sir John Herschel's observations in 1836, possibly even further into the oral traditions of indigenous cultures. But here's the twist. Betelgeuse isn't just a predictable waltzer, it's a cosmic jitterbug. Its brightness fluctuates with an unsettling irregularity, throwing off even the most meticulously documented cycles. This unpredictable behavior fuels the flames of mystery surrounding Betelgeuse. Is it a sign of internal turmoil, a brewing storm within the star's fiery heart? Could these irregularities be a prelude to a colossal transformation, a supernova unlike anything humanity had ever witnessed. Betelgeuse, the fiery giant in Orion, isn't content with a predictable existence. Unlike clockwork stars, it throws curveballs, hinting at a tumultuous past and an uncertain future. In a recent event that sent shivers down the spines of astronomers, Betelgeuse surprised us all with a dramatic dimming, now known as the Great Dimming.
I remember being walked through that fluid with him, and I was trying to look up at him, and I couldn't turn my head to look at him. And he had his hand straight. I knew his voice, but I did not know who it was, but I felt confident and comfortable. And as we moved along this dark blue fluid path,
the Great Dimming. Late 2019 marked the beginning of a celestial whodunit. Betelgeuse, a regular fixture in the night sky, began to mysteriously dim. This wasn't a subtle shift, it was losing brightness at an alarming rate, dropping in luminosity by 0.01 magnitudes a day. By February 2020, the once proud star, typically visible even in city lights, became noticeably fainter, a change visible even to the naked eye. But here's the cosmic catch. When we observe stars like Betelgeuse, we're not seeing them in the present, but in the past. The vast distance, in this case roughly 725 light-years, creates a time paradox. The light we see today left Betelgeuse nearly 700 years ago. This time lag makes studying Betelgeuse a challenge. It's like trying to diagnose a patient based on medical records from the Middle Ages. So, what caused the Great Dimming? Was it a prelude to a colossal explosion? A supernova that would forever alter the night sky? Or is there another explanation lurking within the fiery depths of Betelgeuse?
and that water is incompressible. And so it's just going to react, and immediately it converts into a plasma. And so we can project anything into space. All of that has been accomplished.
Hubble unveils Betelgeuse's secrets. The dimming of Betelgeuse served as a stark reminder of the limitations we face in studying the cosmos. Vast distances and the time paradox they introduce create a cosmic delay, making real-time observations a challenge. But that didn't stop astronomers from unraveling the mystery. Enter Dr. Andrea Dupree, Associate Director at the Center for Astrophysics at Harvard and Smithsonian. Leading a team, she turned to the Hubble Space Telescope, already monitoring Betelgeuse for variations in its outer atmosphere as part of a long-term study. Hubble proved to be a crucial tool. Its sensitivity to ultraviolet light allowed them to peer beyond the star's surface, into the scorching layers heated by churning convection cells. Analyzing Hubble's spectra, like celestial fingerprints, taken throughout 2019 and 2020, revealed an intriguing story. The culprit behind the dimming wasn't a looming supernova, but something far less dramatic, at least for now. Betelgeuse, it turned out, was simply having a bad hair day. Well, a bad atmosphere day, to be precise. The data pointed towards massive amounts of material being ejected from the star's outer layers, temporarily blocking our view and causing the dimming. This discovery wasn't just about solving a cosmic whodunit. It provided a window into the dynamic nature of a red supergiant like Betelgeuse. Their expansion and contraction create a natural ebb and flow of brightness. But the Betelgeuse dimming event showcased a more dramatic ejection that surprised astronomers and highlighted the complexities of these celestial giants. The story of Betelgeuse is far from over. While we may have dodged a supernova bullet this time, the question remains: what's next for this enigmatic star? Hubble's sharp gaze unraveled the culprit behind Betelgeuse's dimming, a celestial tantrum of sorts, focusing on specific light signatures often called magnesium-2 lines. Dr. Dupree's team saw something remarkable. Material scorching hot and dense was blasting off the star's surface at mind-boggling speeds of 200,000 miles per hour. The stellar tantrum didn't just ruffle feathers, it flung massive amounts of material millions of miles into space. Over time, this hot, dense gas cooled, condensing into a dust cloud that shrouded Betelgeuse like a celestial veil. This dust cloud, a byproduct of the outburst, was the reason for the star's dimming. The amount of material lost was staggering. Dupree's team estimated it to be double the usual outflow from Betelgeuse's southern hemisphere, a significant mass loss even for a star constantly shedding material like Betelgeuse, albeit at a much slower pace than our Sun. The sheer scale of this event, the mass ejection and subsequent dimming, understandably sparked fears of a supernova. Betelgeuse's proximity, a mere 725 light-years from Earth, heightened the drama. A supernova here would be a front-row seat to stellar fireworks, a rare opportunity for astronomers. But the big question loomed: was this dimming a dress rehearsal for a supernova, or just a dramatic chapter in Betelgeuse's ongoing story? Several theories emerged. One quite naturally pointed towards a potential supernova, a terrifying prospect given Betelgeuse's supposed twilight years. Another, more comforting theory placed the blame on dust. After all, red supergiants like Betelgeuse are known to shed material, and this dust could be thick enough to block our view of the star itself. The mystery of Betelgeuse dimming deepened with a third suspect, the star's own surface, called the photosphere. Could a change in this layer be causing the dimming? To crack this astronomical whodunit, scientists employed various detective tools. Spectroscopic studies akin to celestial fingerprints revealed a drop in Betelgeuse's temperature. This pointed towards a culprit hiding in plain sight, a colossal dark spot on the star's surface. The evidence was compelling. Betelgeuse's temperature had plummeted by a staggering 170 Kelvin around the dimming event, hinting at dramatic surface changes. But the true hero of this astronomical saga emerged: the Hubble Space Telescope. Hubble's canine provided the key piece of evidence. Its observations painted a clear picture. The culprit wasn't a death knell for Betelgeuse, but a massive tantrum. Betelgeuse had flung a substantial amount of hot material into space, birthing a celestial dust cloud in the process. This dust cloud, a cosmic veil, obscured a portion of the star's surface, effectively dimming its light as seen from Earth. Hubble, with its ultraviolet light vision, unraveled the timeline of the stellar drama. As early as January 2019, Hubble spotted signs of trouble: dense heated material churning within Betelgeuse's atmosphere, months before the dimming. Then in December 2019, ground-based telescopes witnessed the star's southern hemisphere fading. Intriguingly, this material initially shone brighter than usual, before cooling and morphing into a light-blocking dust cloud. This dark cloud paired with the outflowing material was most likely the reason for Betelgeuse's dramatic dimming. So, the case is closed. Betelgeuse didn't enter its twilight years prematurely, nor did it hide behind a self-inflicted dust veil. Instead, it threw a colossal tantrum, spewing hot material and creating a temporary dimming event. While this doesn't completely rule out a future supernova, it offers a sigh of relief for now. But the story of Betelgeuse continues as we keep our cosmic gaze fixed on this enigmatic star. We can only wonder what the next chapter holds: Betelgeuse's colossal tantrum. The Great Betelgeuse dimming wasn't just a celestial hiccup, it was a cosmic tantrum of epic proportions. Betelgeuse expelled a mind-boggling amount of material, 400 billion times more than a typical stellar sneeze, coronal mass ejection. This colossal burp, estimated to weigh several moons, thrust Betelgeuse into the astronomical spotlight and forced us to reevaluate our understanding of stellar mechanics. What does this monstrous ejection mean for Betelgeuse and the future of massive stars? Traditionally, red supergiants like Betelgeuse shed mass gracefully, like a fading king. But Betelgeuse threw a wrench into this theory, suggesting a far more turbulent and unpredictable end-of-life phase. Could this be a sign of an impending supernova, a celestial explosion that would rock our corner of the galaxy? Some recent studies suggest the possibility of a supernova sooner than expected, maybe even within a few decades.
Was the fact that it's not a constant. It could not be a constant because things weigh heavier on the poles of the Earth.
But Betelgeuse has another trick up its fiery sleeve: the bow shock. As this behemoth barrels through space at a blistering 67,000 miles per hour, it creates a cosmic sonic boom, similar to a ship's bow wave. This bow shock, where Betelgeuse's outer atmosphere collides with interstellar gas and dust, is a testament to the star's dynamic nature and its constant interaction with its environment. Studying this phenomenon not only sheds light on Betelgeuse's current state, but also furthers our understanding of how stars evolve and lose mass. However, the story doesn't end there. Post-tantrum, Betelgeuse seems to be stuck in a cosmic hangover. Its surface has cooled and become less dense, creating an unsettling instability that persists even years later. Scientists suspect a link between Betelgeuse's internal churning, or convection, the titanic ejection, and its current pulsation mode. This ongoing instability raises a crucial question: what internal forces are driving these changes, and how might they culminate in the future? Furthermore, Betelgeuse seems to be shedding mass at a rate far exceeding other stars, hinting at a complex interplay of internal forces. This runaway mass loss, partly driven by its pulsations, seems to be counterbalanced by energy dissipated through shock waves and mass ejections. These observations paint a picture of a dynamic and unpredictable star, forcing astronomers to dust off their models of stellar evolution and take a fresh look at the fiery life cycle of red supergiants like Betelgeuse. The cosmic whodunit continues. The question of Betelgeuse's fiery demise hangs heavy in the air. With all the dramatic changes it's undergone, the colossal mass ejection, its cooling surface, is it on the brink of a supernova? Astronomers grapple with this uncertainty, the recent events sparking a debate about the star's stability and future. The colossal material loss throws a wrench into the established theories, forcing a re-evaluation of the timeline for such an event. Meanwhile, a cosmic stage offers a real-time comparison, the recent supernova SN 2023 IXF. This spectacular explosion, a mere 21 million light-years away in the Pinwheel Galaxy, provides a close-up look at the star's dramatic finale. Discovered by an amateur astronomer using a modest telescope, SN 2023 IXF quickly became a global phenomenon. Telescopes around the world, including Hubble, trained their eyes on this newborn supernova, documenting its every move. The data revealed a colossal star collapsing under its own weight, a core collapse supernova marking the end of a stellar life. But SN 2023 IXF holds another key, the dense shell of gas surrounding it. This hints at a turbulent pre-explosion phase, with the star either shedding mass steadily or experiencing sporadic outbursts. These final moments were far from quiet, echoing similarities in Betelgeuse's recent behavior.
Where there were fluctuations before, and he asked one of the professors about it, and he said, it's a thing that we call intellectual phase locking, where when they get different measurements for the speed of light.
Betelgeuse in context. Studying SN 2023 IXF is like reading Betelgeuse's future. Analyzing the explosion's details from the progenitor star's characteristics to the mechanics of the detonation helps refine models of stellar evolution and supernovae. These insights shed light on Betelgeuse's current state and its potential path. So, when will Betelgeuse explode? The answer remains elusive. Studies suggest Betelgeuse might be in its carbon-burning phase, a precursor to its demise. Some predict a collapse within decades of carbon exhaustion, while others believe it's still in an early stage. Regardless, there's a consensus. Betelgeuse will likely be in the next supernova in our Milky Way, though it could be another 100,000 years. Supernovae throughout history have illuminated the final chapter of stellar lives, from the supernova observed in 185 CE that lingered in the sky for months, to the dazzling SN 1006, the brightest ever recorded. These celestial fireworks offer a glimpse into stellar evolution's grand finale. The most recent Milky Way supernova, SN 1604, meticulously studied by Johann Kepler, serves as another historical touchstone. Betelgeuse, a cosmic enigma, continues to hold our gaze, while SN 2023 IXF offers a preview of its potential future. The true story of this red giant remains unwritten. Will it erupt in a spectacular supernova soon? Or will it surprise us once again? The cosmos holds the answer, and astronomers around the world are waiting with bated breath. Supernovae aren't just celestial fireworks, they're powerful tools for scientific discovery. Take supernova 1987A, a recent supernova in our galactic neighborhood, the Large Magellanic Cloud. Detected within hours of its light reaching Earth, it was the first supernova observed via both neutrino emission and across the entire electromagnetic spectrum. This data goldmine has been instrumental in crafting successful models of supernova behavior and their role in the grand cycle of star formation and death. But what if Betelgeuse decides to put on a light show of its own? Imagine Orion, the celestial hunter, suddenly sporting a dazzling new jewel, a supernova where Betelgeuse once resided. While awe-inspiring, would this stellar explosion pose a threat to Earth? Thankfully, the answer is no. Betelgeuse's fiery demise, classified as a core collapse supernova, won't bring about a planetary apocalypse. These explosions occur when massive stars like Betelgeuse run out of fuel and can no longer withstand their own gravity, collapsing in on themselves. Here's the thing, despite their immense power, core collapse supernovae are incredibly isolated events. Betelgeuse, though relatively close at 725 light-years away, is still a safe distance. The real punch of a supernova is directed inwards, releasing an unimaginable energy in a matter of seconds. An amount our sun would take billions of years to generate. While the visible light show would be spectacular, Earth would only experience a brief, intense burst of illumination, similar to a particularly bright full moon. The brunt of the energy, high-energy radiation like X-rays and gamma rays, wouldn't reach us due to the protective shield of Earth's atmosphere and magnetosphere. These guardians would absorb and deflect the harmful radiation, ensuring life on Earth remains blissfully unaware of the celestial drama unfolding thousands of light-years away. The scientific bonanza of a Betelgeuse supernova. A Betelgeuse supernova wouldn't just be the end of a star, it would be the beginning of a spectacular celestial display and a scientific windfall. Imagine the night sky suddenly ablaze with a new brilliant star. Betelgeuse transformed into a dazzling supernova. For a few weeks or even months, this explosion would outshine the moon, even visible during the day. It would be a breathtaking display, a second sun dominating the daytime sky, captivating everyone from casual stargazers to seasoned astronomers. But beyond the awe-inspiring light show, a Betelgeuse supernova would be a scientific goldmine. These explosions, particularly from massive stars like Betelgeuse, are like cosmic laboratories, offering a front-row seat to stellar evolution's grand finale. One of the most immediate benefits would be witnessing the final stages of stellar evolution firsthand. As Betelgeuse explodes, it hurls the elements forged in its fiery core, including precious heavy elements like iron, out into the cosmos. This process is the universe's recycling program, enriching the interstellar medium with the very building blocks of planets, stars, and even life itself. By studying the aftermath of the explosion, scientists can decipher the fingerprint of these elements left behind, like a cosmic treasure map. This spectroscopic analysis would reveal how Betelgeuse fused elements, how it evolved, and how it ultimately contributed to the ongoing cycle of creation in the universe. This knowledge is crucial for piecing together the grand story of our universe, from its origins to its ever-evolving composition. Understanding the inner workings of a star like Betelgeuse goes beyond just one stellar giant. These insights can be applied to other stars, helping us refine models of stellar evolution and supernovae. This knowledge would allow us to predict future supernovae with greater accuracy and understand the role they play in shaping galaxies and the universe as a whole. The potential impact of a Betelgeuse supernova extends beyond our Milky Way galaxy. Observations from this close proximity would provide invaluable data for astronomers studying supernovae in distant galaxies. By comparing the details of Betelgeuse's explosion to those observed at much greater distances, we can refine our understanding of these enigmatic events across the cosmos. So, while a Betelgeuse supernova might seem like a cosmic doomsday scenario, rest assured, Earth is safely out of harm's way. Instead, it would be a celestial spectacle unlike anything ever witnessed, a scientific bonanza offering profound insights into the universe's grand story. A Betelgeuse supernova wouldn't just be a visual spectacle, it would be a symphony of light, exotic particles, and scientific revelations. While the dazzling display of light would dominate the night sky, an unseen drama would unfold, the emission of neutrinos. These ghostly subatomic particles, notoriously difficult to detect due to their reluctance to interact with matter, would erupt from Betelgeuse's core in a cosmic burst. In the throes of a supernova, neutrinos are produced in staggering numbers, offering a unique glimpse into the heart of a dying star. Studying them would be akin to having a front-row seat to the stellar collapse, revealing the fundamental forces and particles orchestrating this celestial fireworks display. Decoding the secrets hidden within these elusive neutrinos could unlock a treasure trove of knowledge about the universe's most extreme environments. The implications of a Betelgeuse supernova extend far beyond the immediate spectacle. This event could shed light on a cosmic mystery, dark energy, and the expansion of the universe. Remember, it was observations of distant supernovae in the late 1990s that revealed the universe's expansion is accelerating, not slowing down. Betelgeuse, being a relatively close neighbor in cosmic terms of course, would provide invaluable data for studying this phenomenon. It could act as a cosmic yardstick, helping us measure the expansion rate of the universe and the role dark energy plays in this unexpected twist. This knowledge could refine our understanding of these fundamental cosmological concepts, potentially leading to the discovery of entirely new questions about the fate and nature of the cosmos. Earth's cosmic insulation.
But what if we told you that something went terribly wrong? Recently, an unexpected and inexplicable event occurred at CERN, leaving scientists scrambling for answers. Actor and science enthusiast Terrence Howard shared his insights on the LHC's latest developments, offering a unique perspective on the ongoing discoveries and challenges. The anomaly observed has stirred a whirlwind of speculation, theories, and excitement within the scientific community. What could have caused such a shocking outcome? And more importantly, what does this mean for the future of particle physics? Stay tuned as we unravel the enigma surrounding this perplexing incident at the LHC. Terrence Howard recently brought attention to a perplexing incident at the Large Hadron Collider. When CERN scientists pushed the collider to its highest energy levels, they observed an unexpected and puzzling result. Howard highlighted the excitement and speculation within the scientific community as experts proposed various theories to explain this anomaly. This unexplained result occurred when the LHC was operating at its maximum capacity. The observed data did not match predictions, leading to a flurry of activity among physicists. The anomaly has sparked numerous hypotheses, ranging from potential new particles to undiscovered principles of physics. Howard noted that the scientific community is buzzing with theories to explain this surprising outcome. Some experts suggest that the anomaly could indicate the presence of new, previously undetected particles. Others believe it might point to limitations in the current models of particle physics, suggesting that our understanding of the universe's fundamental forces might need revisiting. The implications of this anomaly are profound. If the observed result leads to the discovery of new particles or forces, it could revolutionize our understanding of the universe. Such a breakthrough would open up new avenues for research and potentially lead to the development of novel technologies based on these newfound principles. What caused such a surprising outcome? And what does it mean for our future scientific endeavors? These questions are at the forefront of the ongoing investigation at CERN. The unexpected results challenge scientists to think creatively and explore beyond the established boundaries of physics. The unexplained anomalies at the LHC highlight the ever-evolving nature of scientific discovery. As researchers delve deeper into the data and refine their experiments, the potential for groundbreaking discoveries grows. Terrence Howard's spotlight on this incident underscores the importance of continuous inquiry and the excitement that comes with pushing the limits of human knowledge. The scientific community, fueled by curiosity and driven by these unexpected findings, is poised to unravel more mysteries of the universe. Howard described the Large Hadron Collider, LHC, as a colossal machine, stretching across 2 countries and extending deep underground. Imagine a device so immense and powerful, it redefines our approach to particle physics, he explained. The LHC is not just a machine, it's a marvel of human ingenuity and engineering. Spanning a 27-kilometer ring, it lies beneath the border between Switzerland and France. This enormous structure is composed of superconducting magnets and a series of accelerating structures designed to boost the energy of particles. The sheer scale of the LHC is staggering, representing decades of collaboration among thousands of scientists and engineers from around the world. Howard highlighted how the LHC redefines our approach to particle physics. Traditional methods of studying the universe's smallest components were limited in scope and power. The LHC changes this by allowing scientists to collide particles at unprecedented energies. This provides a glimpse into conditions that existed just moments after the Big Bang, offering insights into the fundamental forces that govern the universe. The construction of the LHC is a testament to what humanity can achieve when united by curiosity and a quest for knowledge. The machine's development required innovative solutions to overcome numerous engineering challenges. From the design of its powerful magnets, which must operate at extremely low temperatures, to the precise alignment of its components, every aspect of the LHC represents the cutting edge of technology. Howard also touched on the captivating stories behind the LHC's creation. The journey to build the collider involved overcoming geopolitical, financial, and technical hurdles. It required international cooperation on an unprecedented scale, with scientists and engineers from over 100 countries contributing their expertise. The stories of persistence, collaboration, and innovation are as compelling as the scientific discoveries the LHC aims to make. More so, the LHC holds the promise of groundbreaking discoveries. It is designed to answer some of the most profound questions in physics. What is the nature of dark matter? What happened in the first moments of the universe? Are there additional dimensions beyond the ones we perceive? By smashing particles together at near-light speeds, the LHC creates conditions that allow scientists to probe these mysteries, potentially revolutionizing our understanding of the universe. CERN, the European Organization for Nuclear Research, stands as a beacon of international collaboration and scientific curiosity. Its origins trace back to the post-World War II era. As Europe was recovering from the devastating conflict, there was a growing consensus among scientists and policymakers that collaboration was the key to rebuilding the continent's scientific prowess. In 1950, the renowned physicist Louis de Broglie proposed the creation of a shared European laboratory to rekindle scientific innovation and strengthen peaceful cooperation. Soon after, in 1952, 11 countries came together to sign the CERN Convention, establishing the organization. By 1957, CERN was officially up and running on the border between Switzerland and France. CERN's mission has always been to delve into the mysteries of atomic nuclei and their components. To do this, particle accelerators were essential. These massive machines accelerate particles to nearly the speed of light and smash them together, revealing the fundamental building blocks of the universe. By the 1980s, the vision for the LHC began to take shape, driven by the need for a more powerful tool to explore deeper into matter's secrets. The LHC was designed as the world's most powerful particle accelerator, featuring a 27-kilometer ring of superconducting magnets and detectors. Its construction began in 1998, a massive project that brought together thousands of scientists and engineers from around the globe. Situated 100 meters underground, the LHC was strategically placed to avoid the complex terrain of the Jura Mountains and to shield it from external influences. This underground location also avoided the high cost of surface land. In 2010, the LHC achieved a major milestone by successfully colliding particles at an energy level of 3.5 tera-electron volts per beam, an unprecedented feat at the time. After subsequent upgrades, it now operates at an even more astounding 6.5 tera-electron volts. Picture two beams of particles racing at nearly the speed of light and colliding head-on. That's the extraordinary capability of the LHC. There are 4 key collision points within the LHC, each surrounded by sophisticated detectors designed to capture and analyze the phenomena resulting from these high-energy impacts. Most of the time, the LHC is busy colliding proton beams, but once a year, it switches gears to collide heavy ions like lead, creating a special annual event. Howard passionately conveyed the significance of these endeavors. Why invest so much effort? Because the quest to understand our universe drives us to push the boundaries of science and technology. Physicists are utilizing the LHC to explore some of the most complex theories in particle physics. They are particularly interested in studying the elusive Higgs boson and investigating a large array of particles predicted by supersymmetric theories. Hadrons, tiny subatomic particles composed of even smaller quarks, are a key focus. These particles form the building blocks of protons and neutrons. The LHC, named for its ability to collide hadrons, produces byproducts that often exist only briefly and can't be studied by any other means. Each collision in this enormous underground ring is akin to a mini Big Bang, offering scientists a glimpse into the fundamental components and forces of the universe. Constructed between 1983 and 1988, the LHC's underground tunnel spans a massive 3.8 meters in width and is protected by concrete. Above ground, there is a building housing essential equipment such as control electronics, compressors, ventilation systems, and cooling devices. The LHC generates around 15 petabytes of data annually, an immense volume of information. To manage this, an international collaboration created a specialized computing grid just for the LHC, which is a technological marvel on its own. The primary mission of the LHC is to uncover the secrets of the Higgs boson, a particle long theorized by scientists, but never observed due to its high mass. The LHC's powerful capabilities were designed to produce multiple Higgs bosons each minute, like setting a trap for an elusive creature. Beyond the Higgs boson, the LHC has delved into other uncharted areas of physics, searching for supersymmetric particles and other unknown phenomena. However, the journey hasn't been without challenges. Shortly after its launch in 2008, a magnet malfunction caused significant damage, delaying operations for over a year. But from 2009 to 2013, the LHC made groundbreaking discoveries, including finally observing the elusive Higgs boson. After its first successful run, the LHC was upgraded and resumed operations in 2015, embarking on new scientific adventures. The second run of the LHC lasted from 2015 to 2018, followed by another pause until it restarted in April 2022 with an enhanced beam energy of 6.8 TeV. This third run will continue to captivate scientists until 2026. During this third run, something extraordinary occurred on July 7th. A mysterious crack appeared in Earth's magnetic field, remaining open for an astonishing 14 hours. This allowed a surge of solar winds from the sun, resulting in massive geomagnetic storms and spectacular auroras. The crack was attributed to a co-rotating interaction region, CIR, from the sun, where solar winds of different speeds interact, creating turbulent plasma structures. Experts assure us that such cracks in the magnetic field are not unusual and usually close quickly. However, recent events show they can stay open longer, allowing some space storm energy to penetrate and potentially disrupt satellites, radios, and power systems. While our magnetic shield generally protects us from these storms, some energy occasionally slips through, similar to living in a house with a drafty window during a storm. Overall, the LHC continues to be a pivotal tool in uncovering the mysteries of our universe, with each run promising new discoveries and insights into the very fabric of existence. The LHC's operation involves not just incredible physics, but also managing vast amounts of data. Imagine a room packed with complex control electronics, compressors, ventilation systems, and cooling equipment. This high-tech environment is necessary to support the LHC's functions. However, the truly astonishing aspect is the data output. The LHC generates around 15 petabytes of data every year. To put this into perspective, 15 petabytes of data is equivalent to about 15 million gigabytes. This massive volume of information poses significant challenges in terms of storage, processing, and analysis. The data is generated from the millions of particle collisions that occur every second within the LHC. Each collision produces a wealth of information about the particles involved and the resulting interactions. To handle this immense amount of information, an international collaboration established a specialized computing grid specifically for the LHC. This grid, known as the Worldwide LHC Computing Grid, WLCG, is a network of over 170 computing centers in 42 countries. It is designed to store, distribute, and analyze the data produced by the LHC. The WLCG is a technological marvel, providing the necessary infrastructure to manage the LHC's data efficiently. The computing grid involves cutting-edge technology and innovative software solutions. Data from the LHC is first processed by the Tier 0 Center at CERN, where initial analysis and filtering occur. The filtered data is then distributed to Tier 1 centers around the world for further processing. Finally, Tier 2 centers, which include university and research institute computing facilities, conduct detailed analyses and simulations. This tiered approach ensures that the massive data load is managed effectively and that valuable insights are extracted promptly. The primary goal of the LHC is to uncover the secrets of the Higgs boson, a particle that was theorized for decades before being discovered by the LHC in 2012. The Higgs boson is essential for understanding why particles have mass. Despite its importance, the Higgs boson remained unseen due to its substantial mass, making it difficult to produce and detect with previous technology. With its immense power, the LHC can produce several Higgs bosons each minute during high-energy collisions. These collisions occur at nearly the speed of light, recreating conditions similar to those just after the Big Bang. The ability to produce Higgs bosons regularly allows scientists to study this elusive particle in unprecedented detail. By examining how the Higgs boson interacts with other particles, researchers can gain insights into the fundamental structure of the universe. the discovery and ongoing study of the Higgs boson have profound implications for particle physics. It confirms the mechanism that gives particles their mass, as predicted by the standard model of particle physics. However, the Higgs boson also raises new questions, such as the nature of dark matter and the potential existence of other unknown particles. The data generated by the LHC is crucial for exploring these mysteries. The quest to explore the unknown realms of physics with the Large Hadron Collider, LHC, can be likened to attempting to capture a rare, elusive creature, one that many believed existed but had never seen. The discovery of the Higgs boson was a monumental achievement, but the LHC's ambitions extended far beyond that. It ventured into uncharted territories of physics, probing for supersymmetric particles and other hidden phenomena that could fundamentally alter our understanding of the universe. The journey, however, was not without its challenges. Shortly after the LHC began operations in September 2008, a significant setback occurred. A magnet malfunction caused extensive damage to the collider, halting experiments and necessitating a shutdown for over a year. This incident underscored the complexity and delicacy of operating such a massive and sophisticated machine. The repair and recovery process was arduous, involving meticulous work to replace and recalibrate the damaged components. Despite this initial hurdle, the LHC resumed its operations from 2009 to 2013. During this period, the collider made several groundbreaking discoveries, the most notable being the identification of the Higgs boson in 2012. This discovery was a major milestone in particle physics, confirming the existence of the particle that gives mass to other particles, as predicted by the Standard Model. It was a momentous achievement that validated decades of theoretical work and experimental efforts. Following this success, the LHC was temporarily shut down in 2013 for a series of planned upgrades. These enhancements were designed to increase its power and improve its detection capabilities. The upgrades included strengthening the collider's magnets, improving its cooling systems, and enhancing the data collection and processing infrastructure. The LHC returned to operation in 2015, entering its second phase, which lasted until 2018. During this second phase, the LHC continued to explore new frontiers in particle physics. Researchers focused on searching for evidence of supersymmetry, a theoretical framework that extends the Standard Model by predicting a larger family of particles. The collider also investigated other exotic phenomena, such as dark matter candidates and potential extra dimensions. After another break for additional upgrades, the LHC resumed operations in April 2022. This third phase features an enhanced beam energy of 6.8 TeV, allowing for even more powerful and precise collisions. This increased energy capacity is crucial for probing deeper into the subatomic world and potentially uncovering new particles and forces. The current phase of the LHC is expected to continue until 2026, promising to deliver even more captivating discoveries. Scientists are particularly excited about the potential to find new physics beyond the Standard Model. This could include evidence for dark matter, insights into the asymmetry between matter and antimatter, and further understanding of the strong force that binds quarks together in protons and neutrons. The LHC's journey has been marked by both significant challenges and remarkable breakthroughs. From its early setback due to a magnet malfunction to the historic discovery of the Higgs boson and beyond, the LHC has continually pushed the boundaries of our knowledge. Its ongoing upgrades and current phase of operation hold the promise of even more revolutionary discoveries, continuing to captivate and inspire the scientific community and the public alike. But on July 7th, during its third run, something truly remarkable occurred. Picture Earth's magnetic field as a protective bubble around our planet. On that day, a mysterious crack appeared in the shield. This wasn't just a brief glitch. It remained open for an incredible 14 hours. Imagine a window left open on a stormy night, letting in the cold winds. This crack allowed a surge of solar winds from the sun, causing massive geomagnetic storms. The result: spectacular displays of auroras lit up the sky. Fans of Stranger Things might liken this event to the emergence of the monstrous Vecna, humorously suggesting he came through this crack. While that's just playful speculation, the breathtaking auroras were a real and undeniable visual treat. Think of the search for dark matter like a treasure hunt where, Instead of finding the actual treasure, you uncover maps that lead to it. These clues might just be hints for more significant discoveries in future experiments. Here's an intriguing twist: dark matter. This mysterious substance, though invisible, constitutes a significant part of our universe. Some of the new particles detected by the LHC might be linked to dark matter. However, these particles are so elusive that they rarely reveal themselves directly. It's akin to trying to see the wind. You can't see it directly, but you can observe its effects, like leaves rustling in the breeze. At the LHC, scientists look for other particles behaving unusually, which might suggest the presence of these invisible ones. The challenge lies in the fact that these signs are often incredibly faint. Detecting them is like trying to hear a whisper in the middle of a loud rock concert. The subtle indications of dark matter are easily drowned out by more dominant signals. This makes the task of identifying dark matter particles exceptionally difficult. However, with the upgrades introduced in Run 3, the LHC's detectors have been enhanced to pick up these faint signals more effectively. These upgrades include improvements in sensitivity and resolution, allowing scientists to detect even the slightest anomalies in particle behavior. This enhanced capability increases the likelihood of capturing elusive particles associated with dark matter. These advancements mean that scientists are better equipped than ever to uncover new clues about dark matter. Each detected anomaly, no matter how small, brings researchers one step closer to understanding this enigmatic substance. The ongoing experiments and data analysis are crucial for piecing together the puzzle of dark matter, potentially leading to groundbreaking discoveries in future runs of the LHC. The search for dark matter at the LHC is like a meticulous treasure hunt. While the actual treasure remains hidden, the maps and clues gathered along the way provide invaluable guidance. The elusive nature of dark matter presents significant challenges, but with the LHC's upgraded detectors, scientists are now more capable of picking up the faint signals that could reveal its secrets. As research continues, each discovery brings us closer to unraveling one of the greatest mysteries of the universe. But wait, there's more. Plans are in motion for an even larger and more ambitious project: the Future Circular Collider, FCC. Think of it as the LHC's bigger, more powerful sibling. This enormous particle accelerator could come with a price tag ranging from 9 to 21 billion euros. However, not everyone agrees with this investment. Some argue that such a substantial sum could be better spent on other significant scientific endeavors. For instance, why not build a giant radio telescope on the moon's far side or launch a space-based instrument to detect gravitational waves? The proposed Future Circular Collider has sparked considerable debate within the scientific community and beyond. While many see it as the next logical step in particle physics, others question the return on such a massive investment. Critics, like well-known physicist Sabine Hossenfelder, argue that this colossal machine might not deliver the groundbreaking discoveries we hope for. It's akin to investing in an ultra-powerful telescope that might not reveal any new stars. They suggest that alternative projects, such as developing advanced telescopes or space-based detectors, might yield more immediate and diverse scientific benefits. Despite these concerns, the FCC represents an extraordinary leap in our quest to understand the fundamental nature of the universe. If built, it would dwarf the LHC, providing unprecedented energy levels and collision rates. This increased capability would allow scientists to explore uncharted territories in particle physics, potentially uncovering new particles and forces that could revolutionize our understanding of the universe. Meanwhile, the LHC is gearing up for Run 3 and even a potential Run 4, promising plenty of exciting science on the horizon. Each phase of LHC operations has brought us closer to solving key mysteries in physics, such as the nature of dark matter, the behavior of antimatter, and the fundamental forces of nature. We are in the midst of a cosmic detective story, piecing together clues one by one, with each phase promising new insights and discoveries. The Future Circular Collider represents both a bold vision and a contentious investment in the future of particle physics. While its potential to unlock new realms of understanding is vast, so are the costs and uncertainties associated with its construction and operation. As the scientific community continues to debate its merits, the LHC's ongoing and future runs ensure that our journey of discovery is far from over. We stand on the brink of new breakthroughs, driven by our relentless curiosity and the ever-advancing frontier of science. Think of these developments like episodes of a gripping series, and we're about to binge-watch the latest installment. One recent surprise involved an anomaly in Earth's magnetic field that stayed open much longer than expected. Imagine discovering a hidden door in your house you never knew existed. This unexpected crack in the magnetic field allowed solar winds to flood in, causing geomagnetic storms and dazzling auroras. What more might we uncover next? Max Laughlin, a prodigious thinker, proposes a rather alarming theory. He suggests that experiments at CERN could have caused a shift in our reality, leading to what is known as the Mandela effect. According to Laughlin, the high-energy particle collisions at CERN might have created a ripple in the fabric of space-time, nudging us into a slightly different version of our universe. The Mandela effect refers to instances where many people remember events or details differently from how they actually occurred. Named after the false memory of Nelson Mandela dying in prison in the 1980s rather than in 2013, this phenomenon is believed by some to be evidence of our transition to an alternate reality. For example, people might recall famous logos, quotes, or historical events differently than they are documented. Laughlin's theory posits that the extreme energies and conditions created during CERN's particle collisions could potentially disrupt the very fabric of space-time. These disruptions, he suggests, might result in our consciousness shifting into a universe almost identical to ours, but with subtle differences, hence the collective false memories. However, while Laughlin's theory is fascinating and captures the imagination, it remains speculative. The scientific community largely views it with skepticism. The experiments conducted at CERN are indeed at the cutting edge of physics, exploring the fundamental particles and forces that make up our universe. They push the boundaries of our understanding, but there is no concrete evidence to support the idea that they can create alternate realities or shift our consciousness into them. The work at CERN has led to numerous groundbreaking discoveries, including the confirmation of the Higgs boson, but its impact on the fabric of reality as we perceive it remains firmly within the realm of theoretical speculation. While the Mandela effect continues to intrigue and puzzle people, it is more likely a result of the complex workings of human memory and cognition than a consequence of particle physics experiments. With the emergence of various theories and public concerns about the experiments conducted at CERN, it's natural for people to worry about safety. One of the primary concerns at CERN involves radiation. To minimize exposure, CERN has implemented stringent safety protocols. Personnel working with particle accelerators and detectors are equipped with dosimeters, which constantly monitor their radiation levels. Areas where radiation hazards exist are strictly controlled, and access is limited to trained personnel. Additionally, the engineering designs of the facilities incorporate robust shielding materials to contain radiation effectively. Chemical safety is another critical aspect. CERN handles a variety of hazardous substances, and they have meticulous procedures for their handling and disposal. This ensures that chemicals are managed safely to prevent any accidents or environmental contamination. Electrical safety is also paramount, with regular inspections and adherence to international standards to prevent electrical hazards. Fire prevention systems are rigorously maintained, with regular drills and safety checks to ensure all equipment is functioning correctly. The safety of CERN's workforce is a top priority. Comprehensive training programs are in place to ensure that all personnel are well-versed in safety protocols. Safety drills are regularly conducted to prepare staff for emergencies such as fires, chemical spills, or radiation leaks. CERN also has an on-site medical service to address any health-related issues promptly, ensuring quick response times in case of accidents or medical emergencies. CERN is equally committed to environmental safety. They take significant steps to minimize their environmental footprint, managing waste responsibly and monitoring air and water quality to prevent contamination. CERN's operations include rigorous environmental monitoring to ensure that their activities do not adversely affect the surrounding area. CERN extends its safety commitments to the public. Access to the facility is controlled to minimize risks, ensuring that visitors are safe at all times. CERN maintains open lines of communication with local authorities and actively engages with the community to address any concerns. They hold public forums and provide detailed information about their safety measures to reassure the community and stakeholders. In conclusion, CERN's commitment to safety is comprehensive and multifaceted. From radiation containment and chemical handling to electrical safety and environmental protection, every aspect of their operations is designed with safety in mind. By prioritizing the well-being of their workforce, the public, and the environment, CERN demonstrates its dedication to conducting groundbreaking scientific research responsibly and safely. Thank you for being with us. Let us know what you think about these discoveries in the comments below, and we'll see you in the next one.